Okay, I'm going to be working 11.7 maximum and minimum values, and we're given here for number 3 this function of two variables. And so what we'll do is we'll first take a look at where could we possibly have maximum minimum values and possibly saddle points. And according to the second derivative test, what we first need to do is figure out where the partial derivatives are equal to 0. Okay, we need to figure out, does this ever happen? So let me take some partials here. The partial of f with respect to x is 2x plus, let's see, derivative of this with respect to x is y, and then derivative of all that 0. So that's the partial with respect to x. I want to know when that's 0. And then over here, partial with respect to y, I get x plus, let's see, 2y plus 1 equals 0. And so I have two equations and I have two unknowns. So what I'll do is I'll just create a little, well, I can do this with substitution, or I can do a little system of equations. I'll do the system of equations. I'm going to write this down. 2x plus y equals 0. I'm going to write this one down. X plus 2y equals negative 1, so I move the constant to the other side. And now what I'll do is I'll just multiply this bottom row by negative 2, and that way I can get the x's to cancel. So we have 2x plus y. So I'm looking at this as like a system of equations from college algebra. Equals 0. Multiplying the bottom row by negative 2, get negative 2x, get negative 4y equals 2. And then add these two equations straight down, and you just get negative 3y equals 2, which means y is negative 2/3. And then you go to get x, so just take any of these equations like this one right here. X plus 2y equals negative 1. Replace y with this. So 2 times negative 2/3 equals negative 1. So x minus 4/3 is negative 1. Add 4/3 to both sides, and you'll get x is equal to 1/3. So if I'm going to have a maximum, local minimum, or a saddle point, this is the only place it's going to happen. It's going to happen at the point which we'll call AB, and it is the point 1/3, negative 2/3. All right, so now what we do, after we figured out where we might have them, is we go calculate this thing called D, capital D. Capital D is basically the second derivative test. It's what we're going to test to figure out if it's a local maximum or minimum. So I'm going to now just write the formula quickly for D. Capital D is equal to the second partial with respect to x times the second partial with respect to y minus partial with respect to x followed by y, that quantity squared. So we had already taken the partial of f with respect to x, but I'll write it down over here again. I'm going to keep this here because I'm going to need that. Partial with respect to x was 2x plus y. Let's take the partial of that again with respect to x, and we just get 2. We had the partial with respect to y was x plus 2y plus 1. Now let's take the partial of that with respect to y again, and we get 2. And we also need to know the partial of f with respect to x followed by y. So I'm just getting this part, and this part right now. Partial with respect to x was here. Now take the partial of that with respect to y. We get 1. So what we get is 2 here times 2 here minus 1 squared, which is 3. So what we see here is this computation of capital D. Notice that the second partial here was a constant, second partial a constant, this second partial was a constant. So even though we found a point A and B that we would originally want to plug in over here, because these were constants, we don't have to. So like if this had x's and y's and x's and y's and x's and y's, then we'd have to plug this in for x and this in for y, and then that would give us our D. But in this case, it doesn't matter. So D, what we get here is D is a positive number, right? It's 3. And if D is positive, we either have a local maximum or a local minimum. The next thing we need to look at then is the second partial of f with respect to x, which was 2, and that's also positive. So if your capital D is positive and the second partial is positive also, then according to the test, that means that this is a local minimum. And it happens at the point, let's see, x is 1/3, y is negative 2/3. And I'm going to go one more step. I'm actually going to figure out what the z is, or the f of x, y value. So I want to plug these into this to actually figure out, what is that minimum value? This is where it happens. This is the x and the y that make it happen in the domain, but I want the output. So I'm going to come in here and plug in 1/3 right here. We get 1/9 plus, let's see, 1/3 times negative 2/3 plus, here's going to be negative 2/3 squared, and then plus this, which is negative 2/3. So let's see what we get there. So I have 1/9. Multiply these together and get minus 2/9. Put these, square that, I get 4/9. And then minus 2/3. I think I'm going to get a common denominator here, so multiply top and bottom by 9. By 3, so I'm going to get negative 6/9. And then I can put all those together. That's 1 minus 2 plus 4 minus 6 all over 9. What do we have here? Negative 1, 3, so negative 3/9, which is negative 1/3. There we go. So that means that if you were to graph this function, I would have a local minimum at this point. Now, I wouldn't be able to tell you whether or not it's the lowest point on the entire graph. I just can tell you that it's locally a minimum value. All right, let's see what number 5 looks like. Let me see what the work for 5 looks like. 5. Yeah, 5 is worth us taking a look at. Okay, so for 5, let me just send a quick text message. Okay, so for number 5, I have f of x, y equals y cubed plus 3x squared y minus 6x squared minus 6y squared plus 2. All right, so let's first figure out where we could even possibly have these local maximums, local minimums, or saddle points. So I'm going to take the first partial of f with respect to x and set it equal to 0. So partial of this with respect to x would be, let's see, here we have 6x y minus 12x, 0, 0. I need that to be 0. The partial of f with respect to y, that would be, let's see, 3y squared plus 3x squared, 0. And then here, minus 12y, and then derivative of that 0. So I need that to be equal to 0 also. Okay, well this looks rather ominous, doesn't it? We want to know when these two things are 0. So let's try and see if we can figure anything out over here. How about over here we try and solve this for y? Or we could solve for x. It really doesn't matter. And then try and plug that in over here. What I'm afraid to do is this. I'm afraid that you might do this. Do that, and then come through and divide both sides by 6x to get y. Let's just see why that's dangerous. 6x, 6x. Cancel out here. You get y is equal to 2. So that seems okay. The problem is here that I need to make a little stipulation that x cannot be 0 here. All right? There's no way x can be 0, or else I'd have division by 0 here. So as long as x is not 0, y is 2 will make this true. Now let's come over here and let's let y be 2. So let's go ahead and do 2 squared is 4 plus 3x squared minus 12 times 2 again. I should have just done that. This is 12 plus 3x squared minus 24 equals 0. Put those two together. That's negative 12. Take it to the other side. 3x squared equals positive 12. Divide through by 3. So x is equal to plus or minus 2. So here's what I've got so far. If x is 2 and y is 0, right? If x is positive 2, and y would be positive 2. That should work. Or I could do x is negative 2 and y is positive 2. So that would also work. And notice that when I let x be positive or negative 2, I am okay over here with this stipulation. This is true. But I still have to consider something here. What if x was 0, right? Because if x is 0, this is true over here, isn't it? If x is 0, that's true. So I'm going to put here, I guess I'll do it here. If x is 0, right, the question is what would our y have to be? This equation would be true. Now let's let x be 0 over here. If x is 0 here, we get a nice, clean, easy equation to work with, right? X, well, not too bad. X is 0, we get 3y squared minus 12y equals 0. I can factor out a 3y, get y minus 4 equals 0. I get y is 0, y is 4. So if x is 0, then y could also be 0, or y could also be 4. So those are all the different cases I have here. I have, as long as x wasn't 0, then y had to be 2, and that forced our x's to be these two values. But if x was 0, then I had two different y values that could happen. And that should take care of everything. Those are going to be my critical numbers. Those are the things I'm going to have to compute for d here. There's my partial with respect to x. This was my partial with respect to y. This right here was the partial with respect to y. And I'm going to be computing d right now, so I'm going to work with these again. This was my partial with respect to x. So let me take the second partial. With respect to x again, I get 6y minus 12. Over here, if I take the partial with respect to y again, I get 6y minus 12. And then I also need for the formula partial with respect to x followed by y. So if I take the derivative of this with respect to y, I just get 6x. All right. So let's look at capital D. Capital D should be equal to the second partial with respect to x, which is this, 6y minus 12, times the partial of f with respect to y twice, which is 6y minus 12 again, okay, and then minus the partial with respect to x followed by y, 6x, but that quantity squared. All right, so we have 4 different points that we need to check to see what's going on at each of these points. So what is d at the point, let's go with 2, 2, will be equal to, let's see, we plug in 2 for x and 2 for y. So 2 for y here, 12 minus 12 is 0, 12 minus 12 is 0, so that's 0, 0 times 0, minus now 6x, x is 2, so 12 squared, 144. This is negative 144, that's less than 0. Also, let's take a look at, oh wait, if it's less than 0, right? If it's less than 0, this is the easy case. If it's less than 0, what do we have? Saddle point. That's all we need to know. So, oh, I'm sorry. Yeah. This is a saddle point. So I'm going to have a saddle point at, when I plug in 2 for x, 2 for y. And then we could go find what the function's value is there. Let me see if I can get that. 2. Yeah, they don't do it. The book doesn't do it. So I'll just leave it to you. Just go plug in 2 for x and 2 for y into the original function. Figure out what the z coordinate would be. Okay, now I also need to check d at -2, 2. Let's see if that changes anything. Well, I'm plugging in y is 2 into here. I'm still going to get 0, 0. So that's still 0. Minus, when I plug -2 in for x, I get -12. I square it. I still get minus 144. So that's still less than 0. So I have a saddle here. Another saddle. So I'm going to put up here next to this saddle at -2, 2. Who knows? We'd have to plug in to get that. So far we have 2 saddle points here and here. These are done. Now let's try d at 0, 0. This should be easy to plug in. If I plug in 0 here, I get -12, 0 here, -12. -12 times -12 is 144. Minus, if I plug in 0 here, it's all gone, so minus 0. This is a positive number. Oops. Yeah, this is greater than 0. That's what I wanted to say. Since it's greater than 0, we actually need to go check now what was the second partial with respect to x, twice, right, at 0, 0. So come up here. This right here was the second partial with respect to x. What happens if I plug in 0 for y right here? I get -12. And whenever you have d being positive and the partial with respect to x twice being negative, this means we have a local max. And this local max is happening at the point 0, 0, and then I think it'll be easy to plug 0, 0 into the original function, even though it's not up there. Let me just look at the original function. 0, 0, 0, 0. We'll get 2. All right, so I've taken care of these. Now I need to go look at 0, 4. So let me take a look at 0, 4. Calculate d. D at 0, 4. Okay, so I'm plugging in 4 here. 6 times 4 is 24. Take away 12. I get 12. Same thing's going to happen here. 12 minus 0 into this for x. We get 0. This is 144 again. Okay, so since I have that, I now need to go check what's that second partial with respect to x doing at 0, 4. So I didn't do the same notation here, but you understand what I mean. Just plugging 0, 4 into this. And notice that if I do that, plug in 4 for y, I get a positive number. I get 12, greater than 0. So this is different than the last one. See, we got -12 here. So this tells us we have a local minimum. And at the point 0, 4, and then question mark, you could go figure out what that is. That's it. We had 2 saddle points, 1 local maximum, 1 local minimum. All right, 7, I think 7 I'll let you do on your own. 9 looks fun. I don't know if it's going to be. It seems kind of easy. But let's look at 9. Okay, so for 9, f of xy equals e to the x cosine y. So let's take a look at these first partials. Try and figure out when they're 0. So partial of this with respect to x is just, derivative of e to the x is itself, and then cosine y is a constant, so it's just this. And then if I take the partial with respect to y equal to 0, partial of this with respect to y is just negative sine y, and then e to the x is a constant, so negative e to the x sine y equals 0. All right, so what we have now is that we're trying to figure out when this times this is 0, which means I can set each of the factors to 0. This will never happen. E to the x is never 0. Cosine of y is 0 we'll deal with in a second. Same thing with this. That's never 0, so we need to know when sine y is 0. So we actually need to know when both cosine y and sine y are both equal to 0, right? So let's look at this one right here. What will make this true? Cosine of y is 0. Cosine is the x-coordinate. So we get here and here. Then over here, sine y equals 0, which would be here and here. So I think it's obvious from this that there's no way that I can make them both 0 at the same time. I can make this 0, this true, by picking any of these points, right? Any of these angles. How would we say this? This would be pi over 2 plus pi n. That's what y would have to be equal to. You take pi over 2 and you just add any half rotation, either direction. That's what that means. Or over here, you're saying y must be equal to 0 plus pi n, which means you start at 0 and just add half rotations. And so there's just no way that those two are ever going to match. And so there's no critical numbers. That's it. So you don't have any local maximums, you don't have any local minimums, and you do not have any saddle points. Okay, 11 looks like a mess. Let's let 11 be the last one I do for this. Just tired today. Can't get it going. It's Monday. Okay, I'm working on number 11 here. This is actually the second time I'm working through it because the first time it was just kind of a disaster. I ran out of space on the board and I was having trouble with it. So here's the function. And what I'm going to start off with is first taking the partial of f with respect to x. The problem with this one is that these derivatives are ugly. So partial with respect to x, we first have to recognize we have a product rule right here. So I take derivative of this with respect to x, get 2x times e to the y squared minus x squared. Plus, then I take derivative of this with respect to x, which gives me a negative 2x e to the y squared minus x squared times x squared plus y squared. So remember when you take the derivative of this, it's itself, that's this, then times derivative of what's up here with respect to x, which is negative 2x, then times the first function. And then on that, recognize, if you could please, that they both have a 2x, they both have an e to the y squared minus x squared. So I'm going to pull out a 2x and then an e to the y squared minus x squared. What I'm left with is over here a 1. And then I have a minus, because I pulled a positive 2x out, a minus and then this. So minus x squared minus y squared when I pass that through. So that is the simplified version of the first derivative with respect to x. When I take the, should I set that to 0 now? Yeah, let's just set that to 0. If I want to know when that's 0, what I do is I set there's a bunch of different factors here. I set 2x to 0, that gives me 0. I set this to 0, which is never going to happen, and I set this to 0. So I have from here 2x must be 0, and I have that 1 minus x squared minus y squared must also be 0. From this I get x is 0, and from this I get 1 must equal x squared plus y squared. So I don't really know what's going to make that true yet. Now let me try and get the partial of f with respect to y in here. So if I go up here with respect to y, it's almost like this one was. Take derivative of this first one, it's a product rule again. So 2y e to the y squared minus x squared plus, now derivative of this is itself, derivative of what's up here is 2y, so 2y e to the y squared minus x squared, but then times the first part, x squared plus y squared. Again, factor out this time a 2y e to the y squared minus x squared, and you're left with this time a 1 plus x squared plus y squared. Set that equal to 0. And again, you set this to 0, this to 0, that to 0. You get 2y equals 0. The other one, this can never be 0, and this one right here can also never be 0. Check that for yourself here. Look, if I just move those over, make that a -1, that can never be true. So don't have to worry about that. And that's good because this tells me y must be 0. So what I know right now is that for my critical numbers of this thing, my y coordinate must be 0. So y must be 0. And that tells me from this first piece, if y is 0, from this one right here, if y is 0, what would happen here? If y is 0, what do you get? Well, we could actually do it right here. If y is 0, you get x squared is equal to 1, which means x is plus or minus 1. Or if, minus 1. Or, right here, x could be 0, and this would make the first equation 0. So you could also have x equals 0. So here's what I've got. I could have x is 0, y is 0. I could have x is 1, y is 0. I could have x is -1 and y is 0. Those are my three critical numbers. Now I'm going to get a lot of this junk off the board. Okay, this piece we don't need anymore. This piece we don't need anymore. So now what I need to do to calculate capital D is I need to take some more partials. So let me do the partial of f with respect to x twice. So I'm going to be looking at this and taking derivative with respect to x again. And the issue you run into is that you've got a product rule here, but you also have a product rule here. So when I do the derivative of this piece over here, times this, then plus derivative of this times this, when I do that first one, I have to do a product rule. So what is the derivative of this? It is 2, because I'm doing product rule right here, 2 e to the y squared minus x squared, plus the derivative of this with respect to x, which is -2x e to the y squared minus x squared, times this. I'll put it in parentheses. Okay, that's derivative of that. So all of that times this plus the derivative of this with respect to x, which is just -2x, times this, 2x e to the y squared minus x squared. What a mess that is. All right, let's do the second partial here with respect to y twice. So I'm doing this one right here. Same thing. I have a product rule here, but I also have a product rule here. So I'm going to do that little product rule here. It's derivative of 2y is just 2 times e to the y squared minus x squared. And then times, plus, because I'm doing product rule, plus the derivative of this, which is itself times derivative of what's up here, so 2y e to the y squared minus x squared. Finish off the product rule times this, 2y. That is just the derivative of this first piece times this piece, 1 plus x squared plus y squared. And then plus derivative of this with respect to y, 2y times this piece, 2y e to the y squared minus x squared. Sorry about the choppy video. I've got a lot of things going on today. So I think where I was I was going to find the partial with respect to the second partial, which we'll need for calculating d with respect to x then y. So I'm going to be looking at this piece right here. That's your partial with respect to x. And I'm going to be taking the derivative of this with respect to y. So the good news is that I still have product rule, but I don't have a product here because 2x is a constant. So it's just derivative of this with respect to y, which is everything you see there times 2y. So 2x e to the y squared minus x squared, then times 2y. Then times this, 1 minus x squared minus y squared. Then plus product rule, derivative of this with respect to y, which is negative 2y. Then times this right here, which is 2x e to the y squared minus x squared. All right, that's it. So let me highlight the things we have. We have the second partial with respect to x twice, second partial with respect to y twice, second partial with respect to x then y. And now what we need to do is compute d. So in terms of space on this board, let me try and get d right in here. So d, and let's try it at 0, 0 first, will be what I get when I plug 0 for x, 0 for y into this whole thing, times 0 x, 0 y into this, minus 0 for x, 0 for y into here, squared. So what happens when I plug 0 for x and y in here? First of all, notice this is all gone, right? Then this is going to be e to the 0. E to the 0 is 1. So this is just going to be 2 plus nothing. So this is just 2. And then I have, let's see, times this. This is going to be 1. Something ain't right here. Zero, zero. Something is off. Oh, yeah. No, we're good. Okay, so 0, 0, we're going to eat. So 2 times e. No, something still doesn't look right. 0, 0, this is 1. And then here, this is all going to be 0. Don't recall that happening. Oh, all right. Take a breath, Robert. Okay, 0 for x, 0 for y here. This is gone. This is 1. This is 2. So I have 2 plus 0 in brackets. This right here is a 1 times 1 plus, and then this right here gets zeroed out. Okay, so 0. That's just a 2. 2. Okay, now let's plug 0, 0 into this one. Right here. So right here, again, we get 2 e to the 0 is 1, so we get 2 here. That zeroes out. This is a 1. So this is times 1. And then plus, and that gets zeroed out. So that's 2. Then we plug 0, 0 into this, which I believe everything goes away. Let's see, this is 0. That whole thing is 0, so that whole thing is gone. This is 0, so that whole thing is gone. So minus 0 squared equals 4, which is greater than 0. So d is greater than 0, so now what I need to do is check this piece right there. And so I know that f(x) is greater than 0. So we should have a local minimum at 0, 0. So we have a local minimum. I'm going to put local minimum. And now let's go check. Now you can figure out the point. Just plug 0 into the whole thing. Let's try 1, 0. So So if I'm plugging in 1, 1 for x, 0 for y. Let's see what we get for d. 1 for x. So if we go 0y, right here, 0 minus 1 squared, that's negative 1, 2e to the negative 1. Now if I'm plugging in 0 for 1 for x, so that's going to be negative 2 here. It's going to be 2. 2 times negative 2 is negative 4, so I have negative 4 and then e to the negative 1 again, right? But that's all times, let's see here. I plug in 1 minus 1, that's going to be 0 minus 0. So that's 0. The whole thing's gone. So this whole thing is gone. Plus, let's see here. This is going to be negative 2 times 1, so negative 2. And then this is going to be positive 2 e to the negative 1. So that just gives you negative e to the negative 1. Or negative 4 e to the negative 1. So that's the first part. Sorry, that's just the first part. Go back in here. This first part is negative 4 e to the negative 1. Now I need to plug in what I get when I go 1, 0 into this. So if I plug 1, 0, I get 2e to the negative 1. And then over here, if I plug in, look, y is 0, right? So this is all gone. Let's put that in brackets. Over here, there's a little bit of a difference. 0 here, 1 here, I just get a 2 there, so times 2. Then if I let y be 0 here, it's all gone. That's all gone. So I just get another 4e to the negative 1. This time it's 4e to the negative 1, not negative 4e to the negative 1. Then if I plug in 0 for y here, check this out. 0 for y here kills this off. This all goes to 0. This all goes to 0, so I just get minus 0 squared. And this is equal to, well, this right here is a positive number. This is a negative number. They multiply to be negative. This is a positive number. This is a positive number. They multiply to be positive. Negative times positive is negative. So I have a negative number minus 0. This is a negative number. So I can just tell you right now it's less than 0. So I know that this is going to be a saddle point. And I'll let you check it yourself. This should also be a saddle. And that's it for number 11. That's kind of a tricky one because the derivatives are so messy. All right, let's take a look at 23. I'm only going to probably do one of these because time. Okay. Which one of these do I want to do? 21, 25. I'll do 23. So this time we have some function of x and y, and it is x squared plus y squared minus 2, and I'm looking on this region. It's a closed triangular region D with these vertices. So I'm going to draw a picture of the domain of this. It has 0, 0, 0, 2. I'm looking at the wrong one. No, this works. I was looking at 24. This point's there, 2, 0, and 0, negative 2. So it's a triangular region that goes here, 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 and it's everything inside here. So what I'm going to do first is what we've been doing. I'm going to find the partial with respect to x first, set it equal to 0. Partial with respect to x is 2x minus 2 equals 0. That has a pretty easy solution of x is 1. If I let partial with respect to y equals 0, I get 2y equals 0, which means y equals 0. So I'm looking at the point 1, 0. The point 1, 0 is in here. It's right here. So I do need to keep this point in mind at the end, not yet. Just for now, keep this in mind. I do not need to calculate D because this is a closed bounded region. We don't do that capital D, all right? Don't confuse this capital D with domain with the capital D that we were using in the previous problems. So just remember, I've got to come back and check this. I think I'm going to put that point up here. 1, 0, this is a critical point. And then the next thing I'm going to do is I'm going to break this region up into 3 sections. I'll call it L1, L2, and L3. So let's look at L1. For L1, we live on this line. That line has the equation y equals negative x plus 2. So I just found y-intercept. Slope is down 1 over 1, so that's the equation of it. So every point that lives on that line has an x-coordinate of x, has a y-coordinate of negative x plus 2, and x must live inside the interval. So it must be between 0 and 2. That's my x restriction. So what I'm going to do now is I'm going to go back up to the function f of x, y, but I'm going to rewrite it as f of x negative x plus 2 because I'm replacing my y values with negative x plus 2. So I rewrite that x squared plus negative x plus 2 squared minus 2x. So I replace the y in here with negative x plus 2. Let me go ahead and multiply this out. X squared plus, let's see, when I square this I get x squared minus 4x plus 4, then minus 2x, which is 2x squared minus 6x plus 4. So when I'm restricting myself to this line, this function of 2 variables becomes a function of 1 variable, and I'm restricting it on closed intervals. So I just go back to Cal 1 and I figure out, how do you find the maximum of a function on a closed interval? Well, you take its derivative. You set it equal to 0. You also figure out where the derivative is undefined, but this is a polynomial, so the derivative is going to be nice. The derivative of this is just 4x minus 6. Set that to 0, you get x is 3 halves. So x would be 3 halves. So when we go back up and we look at this point, we have x is 3 halves. The y-coordinate must be negative 3 halves plus 2. So this is 3 halves, and then, what is this? This is 4 over 2, so this is going to be 1 half. So that's another critical number. 3 halves, 1 half. Now what I'm going to do is I'm going to look at L2. So when I'm on L2, see at the end I'm going to compare all these numbers. Okay? But for now, let me just say. Come on in. You got a question?
Yes, sir.
You mind you let me finish this real quick?
Yes.
Okay. L2, we have that y must be 0. I'm sorry, x must be 0. So our points are going to look like this. 0 for x, our y coordinate is free because we can be any y, right? X has to be stuck. My y coordinate has to be stuck between negative 2 and 2. And so I rewrite the original function 0y, replace all my x's with zeros. My y's, just leave them as y, so I just get y squared. And wow, I mean, I don't even really need to go through the calculus part of this because I can already tell you where that's going to have max or minimum values. But I'll do it anyway. The derivative of this equal to 0 is going to be 2y equal to 0, and so you get y is 0. And that lives inside there, so we do have the possibility of 0 for x and then a y value being 0. So that's another critical number. 0, 0. And then finally, we need to look at the L3, which would be this right here, which would have the equation y equals x minus 2, which means our points look like this. And if we plug in x minus 2 into our function, we get x squared plus x minus 2 squared minus 2x. This is x squared minus 4x plus 4 plus 2x, which is 2x squared minus 2x plus 4. Now I do my, oh, I forgot to do the restriction. X is restricted between 0 and 2 again, because I'm only going to go from here to here. Take my derivative, set it to 0. I get 4x minus 2 equals 0, which is going to be x is a half. And once I know that x is a half, I can come back up here and look at this and say, all right, if x is a half, then y has to be a half minus 2. So that's going to be a half and then 3 halves, negative. So that's another critical number. 1 half, 3 halves. Now, we also have to check all the endpoints of these intervals, but those points we can obviously see from this picture. The endpoints would have been, or the corner points would have been 0, 2, 2, 0, and 0, negative 2. So what we need to do now is take every single one of those points, all these critical numbers, plug them into this function. The one that gives us the biggest output is the absolute maximum. The one that gives us the smallest, most negative number is our absolute minimum. So what are they? I won't go through the work. We actually have a maximum. Where the hell is it? Make sure I've got these. Absolute maximum actually occurs at these two. We plug either one of those in, and we should get 4 to come out. So this is going to be our absolute max. Happens at 2 different values. And then an absolute minimum actually happens at this one right here. And when we plug those in, we get negative 1. This is our absolute minimum. And that's it. All right, well, I'll let you do the others yourself and see how you can do with those.